we covered most of acid bases. We actually had a assignment due yesterday, or we have assignment due tonight on it. But I do want to cover a couple of things that I think we should just touch on a little bit more in depth, especially from the problems. Remember, we have 2 different office hours, one on Tuesdays and one on Thursdays. So this afternoon, if you have any questions, please feel free to come jump in, and we'll go through your problems together as long as we're there. If you come in late, what we've been doing is it's been lasting 30 to 45 minutes because we exhausted most of everybody's questions. So, you know, come in, ask questions, and we'll stay there as long as need be. Okay, so when we're looking at acids and bases, one of the things that we talked about was Lewis acids and bases. But the way they show up in reactions is slightly different. So let's look at a few examples. So if we look at this example, just this first step, you know, if we change that and put in what's going on, boron and aluminum are characteristic Lewis acids because they have an empty orbital. So these are both aluminum, boron, indium, although you won't see indium too often, are all stable with 6 electrons. So they don't have an octet, but they are stable in that case, which gives it empty orbital, which means then the electrons can just go from the donor, in this case a carbonyl, and we can end up with this, which doesn't look overly stable. It does have a potential second reaction, but this is also stable enough to be in equilibrium and sitting around. What this does, if we think about what this is doing in this Lewis acid, is potentially it's actually activating this position. Right, because we've taken that electron density away from the oxygen, even though there's a dipole moment over here with a partial positive, I've increased that partial positive in the second. We'll see this more. You'll see this more in organic too, but it's important to understand why you would use a Lewis acid. We can also have examples with nitrogen. Again, we have an empty orbital. The result in that if we want to draw that one out, look at the reaction. Again, the boron has an empty orbital. So we just get a one-step donation of electrons to the boron. Boron ends up negative. I left it out up here, make sure you get the negative there. So we have positive, negative. In this case, what we're doing is we're actually making this proton much more acidic. Okay. So we do the Lewis acid-base reaction with the boron to get a change in reaction. Besides these, there's a few others that you'll come in contact with as we do reactions. One is zinc, +2, to act as Lewis acid. Magnesium, again, +2. Calcium. And so although there are Lewis and acid base reactions that result in a product that you want, often you see Lewis acid base reactions as being things that activate or modify a reaction for a second step. So in this case up here, we activated it to get a more electrophilic position. And the second one, we've activated it, now it's more acidic. With the zinc, magnesium, and calcium reactions, in most cases, you're not trying to make a bond with the magnesium, zinc, or calcium. You're actually using those to activate the reaction to do something else. And we'll get to specific examples later. Okay. Any questions about Lewis acids and bases? Because of the importance of nitrogen containing compounds in biological systems, let's go ahead, and the book, the Soderbergh book, actually has a whole section on this. So let's talk about it briefly. If we think about, water picking up a proton, we end up with a pKa, around 1, around -1, around 0. If we look at a nitrogen containing compound like amine, again, we have the lone pair. Here we had 2 lone pairs. We end up with a nitrogen positive, but the resulting pKa here is around 10. So one of the things that nitrogen containing compounds can be in biological systems is a way to transfer protons without an increased acidity. Now, this is important in biological systems because you want more or less neutral systems, right? You don't want highly acidic or highly basic solutions. So we often, not anytime, but often you'll see nitrogen used as what we would call a proton sink, right? It's a proton transfer agent. Anybody familiar with heat sink? Okay. In a computer, you'll have something that's called a heat sink that absorbs the heat from the processor, right? To keep the processor cooler. So as the processor heats up, the material heats up, the conductivity goes down, and the computer becomes less efficient. So to draw the heat away from the processor, they actually will usually have some type of heat sink, something that will conduct heat to usually a piece of metal, and then that can then draw the heat away from that, and then that heat can be dissipated either by blowing air across it, or in smaller devices, just by taking that heat and pushing it out to the actual device. You can feel it in the metal. Those are heat sinks, and what that's doing is make it more reactive. Nitrogen containing compounds are often thought of as proton sinks. They are places where protons can be used to be transferred. And so because of that, let's talk about some of the acidities of different proton species, nitrogen species, and why they're different. One of the first ones is amines, and now we've looked at amines with, if we look at the amine pKa of this species, we get there with a strong base is actually deprotonation of the proton on the other side, mainly because there are no protons attached to the nitrogen. right? And our pKa value here, 23 to 25. But when we have a proton attached to the nitrogen, we can actually get to the negative proton here, and our pKa is around 20. So that proton there is a little bit acidic. And the reason that is that if we look at that nitrogen, we can delocalize that negative into that oxygen. And in fact, if we look at the species beforehand, we can delocalize that negative charge, lone pair, up to the oxygen. So what that means in this compound, right, is since that means that these lone pair here has a low basicity, right? It doesn't react very well as a base. But that if we have a nitrogen with hydrogens attached, that these hydrogens, right, are weakly acid. So I can deprotonate one of those hydrogens, but the nitrogen. So on an amide, again, that is an amide, right? An amide becomes something that's not very basic. It doesn't abstract protons very well. That's important as you look at some biological systems. There's lots of amides. It can be protonated, but it's a weak base. You have to have a strong acid, but it tends to be slightly acidic, right? A little bit less acidic than a ketone or an aldehyde. And when we look at amines, and let's compare this one and so when we compare the just normal amine to one that is adjacent to an aromatic, okay, so this is an aniline compound. When we look there, looking at the conjugate acid, so we react those with an acid. Again, we use the pKa's to give us the relevance here. Here we have a relative pKa of about 10, right? We saw that before, the difference between hydronium being about -1 to 0, and then the amine. So we get about 10, but when we look at the aniline form, our pKa is much higher. If we look at the resonance here, what's happening is we can resonate because of this resonance, we have the base is less basic, and then the acid is more acidic, right? So when we go to aniline, right, we get a little bit higher base, so higher acidity of the conjugate base. So that means that aniline is less basic. Right, because this is more acidic. And that has to do with the resonance of that lone pair through the ring. Okay, that lone pair is tied up, making it less basic. Where in the amine, it's isolated. So in this species, the nitrogen is isolated. Yes, ma'am. In this case, what it's doing is it's taking that lone pair. So it's taking this lone pair and actually tying it up. So if we think about it, the resonance here is more stable, but that makes it less reactive here, right? Since that lone pair here is tied up into that resonance, that makes this reactivity less, which then if I make it react, right, it makes it more acidic. Okay. And again, that's why it's less basic over here, but more acidic over here. The stability is here, not here. One of the other compounds that we should introduce you to, because again, all nitrogens are not the same. Aniline is a very common species in biological systems. One of the other ones is pyrrole. So you'll see this in DNA base pairs and other systems, such as a lot of your hormones and those types of compounds will have these. Pharmaceutical compounds will have these. So in this case, we actually get a pKa that's much higher, so 0. So this is about that of a pronium, of a hydronium. So if we think about this one, right, why is that going to be so much higher? And it has to do with the fact that the lone pair is actually part of the aromaticity. So if we look at this species over here, horrible drawing. Did I put too many? That in this species, that nitrogen then is actually sp2. It's sp2 because if it is sp2, right, then it's aromatic. So if we think about this species, what we have here is if all of those atoms are sp2, then what we have is a continuous ring system, or continuous pi system. And then if we count of our electrons, we have 2, 2, and 2. So we end up with 6 pi electrons. Right? So by Huckel's rule, that's aromatic. So therefore, the lone pair so the lone pair is actually part of the aromatic stability. And this is one of those cases, if you looked at that nitrogen would be sp3. But if it was sp2, the whole molecule would be more stable. So in that case, right, since you can gain aromaticity, this nitrogen is going to rehybridize from sp3 to sp2 because it makes a more stable molecule. If we look up here at this one, right, that nitrogen out here and the lone pair on that nitrogen, not what I meant to hit, stop that. Okay. This lone pair, right, is outside of the aromatic ring. This is the aromatic ring. And so therefore it's isolated from that aromatic. It can resonate into it, but that lone pair is not part of that aromaticity. In this pyrrole compound, that lone pair is essential to aromaticity. So if I take this lone pair away, what have I done? The molecule is no longer aromatic. So if we look at the protonated form, now I have no lone pair. That nitrogen now has no choice, right? It's going to be sp3. And so this is non-aromatic. So in the case of pyrrole, I'm not just going from, neutral species to protonated species. I'm also going from aromatic, and again, think about aromatic is more stable, to non-aromatic. So therefore, the pyrrole is a much more acidic species than the other nitrogens because I'm breaking up the aromaticity. And again, as you go through and look at biological systems, you'll see lots of nitrogen-containing compounds. And in most cases, the nitrogen is a proton sink. It's more stable to put the proton on the nitrogen than it is on the oxygen. But not all nitrogens are created equally, right? In alcohols and carbonyls, they're actually closer to the same acidity than in nitrogens. In nitrogens, we have a broader difference between the acidity of the conjugate bases of conjugate acids of nitrogen containing compounds. Okay, so for the quiz on Thursday, that's where we'll stop. We're on acid base, so we'll look at it'll cover the basics of reaction mechanisms, okay, and then it'll cover acid base reactions. We'll go ahead and move forward into nucleophilic substitutions. This will be on the next exam, but it won't be on the quiz on Thursday. So in nucleophilic substitutions, right, what we're doing is taking a nucleophile and generically we're taking a nucleophile and we're going to substitute that nucleophile for a leaving group. Okay, so substitution, we're not doing a nucleophilic addition, we're not adding it, we're substituting it. So therefore, we're going to replace a leaving group with a nucleophile. So in generic, it's just nucleophile goes electrophile, leaving group leaves. The question is that going to be a one-step process? where the nucleophile comes in, attacks the electrophile, leaving group leaves, making a new bond to the nucleophile, plus now I have a leaving group. I'll just do it neutral like that, all in one step. Going back to our kinetics and thermodynamics, right? This would have one transition state. Or is it a two-step process? In this case, the electrophile and the leaving group in a first step, creating the electrophile plus the leaving group, and then the nucleophile coming in, and let's go ahead and make it negative just so we can balance that all out. So first step, leaving group leaves, takes the electrons with it. Second step, nucleophile attacks the electrophile, and we end up with the leaving group. Now, if we look at these, right, if we look at just the starting materials and the final products, we get the same, more or less the same thing. So generically, just thinking about this, we start with a nucleophile and a substrate. We often call this the substrate that has an electrophilic position. And then we end up with substituting the nucleophile for the leaving group. Now there's several different things though, if we look beyond just the generic no difference between these two, that give us different subtle differences between these products. So it's important to be able to predict whether something's going to go in SN1, I mean one step or two step, SN2 or an SN1. We'll talk about the differences between those. Okay. So this is what we're looking for nucleophilic substitutions. We're going to be substituting, and the big question is it a one step or a two step? So let's look at one step process. Sorry, I'm going to start simpler than this. This will be our second step. So in the first one, we have a nucleophile attacking electrophile. We have a partial positive here because we have a dipole moment going to the bromine. And a leaving group leaves. So a nucleophile is attacking the electrophile, and my leaving group is leaving. Some people don't like the attacks, the way I learned it. and I don't think it's that offensive. The nucleophile is giving its electrons to electrophile, if you want to talk about it that way. And the leaving group leaves. And again, if you're a verbal learner, I would just say this over and over again in your head. Now, this is a one-step process. So both of these occur in that rate determining step. So if we look at what this looks like on our energy diagram, we just have one transition. And the transition would be the nucleophile coming in while the leaving group, the bromide in this case, is leaving, right? So this is our transition state. So if we have partial negative, right, positive. So this is the energy diagram, right? Here's our coordinates. For this reaction to go forward, right, we'd want a delta G that is negative. The delta G is not negative, what's going to happen? The leaving group's going to come back in and kick off what was originally the nucleophile, right? So this reaction is reversible. The bromide could come back in and kick off the hydroxide if the hydroxide is more stable than the bromide, right? But which one's going to be more stable? Bromide negative or hydroxide negative? The bromide negative, right? So therefore, this is going to proceed forward. The other thing we need to think about here is kinetics. So this is our thermodynamic reaction coordinate. And then we need to think about kinetics, right? So we want to look at the rate law. And for this one, right, the rate law is going to be equal to, there's only one step, so therefore it's going to be equal to some constants times the concentration of our hydroxide negative, right, and our concentration of our substrate. And substrate just means what we're acting on. So in this case, it's the CH3. So is this a first order or second order reaction? How many things are involved in the rate determining step? Well, there's only one step, right? So therefore, both things are involved in that one step. So therefore, this is a second order reaction. If I change the concentration of the hydroxide, the reaction will go faster. If I change the concentration of the substrate, the reaction will go faster. That's what it means by rate, right? If I change the concentrations, and the little brackets means concentration. If I change the concentrations of either of these, so if I double hydroxide, the rate will double. If I double the concentration of the substrate, I'll double the rate. If I double both of those, I'll quadruple the rate, right? So that's what this is saying. Now, it turns out that this kinetics, this rate law, is how we get the name for this. Okay? And this is where people get confused. So you have to remember it's the rate law, not the steps. The name for a one step is substitution. That's the base type of reaction. Nucleophilic, because you can have electrophilic. We won't see many this semester. So it's classified as substitution nucleophilic second order, or SN2. What do you think people want to call this? SN1, because it's a first step. Can't think that way, right? You got to know what the 2 is for, and the 2 is second order. So a one step is called SN2. So that's the reaction we're looking at here. It's an SN2 process. We have the nucleophile coming in, attacking the electrophile, leaving group leaving, right? All in one step. we get one transition state, and our rate law is second order. So therefore it's called SN2 process. Now there's some other things that are important here. For this to occur, those electrons have to be put into something, right? And so therefore one of the things that we need to know about this is our spatial arrangements. So if we look at our carbon here, right, we've got our boron, our lone pairs, and this is going to be an sp3 overlap. And that's the bonding side. Different color here. But then on this side, right, we have the anti-bonding orbital. And we introduced that way on early, right, when we showed the combination of the P's and the S's, that a P is going to have two lobes, right, with a node. And so therefore we're going to have this bonding and anti-bonding. And I said it would come back up. Well, this is where it's coming back up, right? That anti-bonding orbital has no electrons in it. Remember that we always take two orbitals and we have one that goes down to create a bonding, and we have another one goes up to create an anti-bonding. We put electrons in the bonding, that makes a bond, and then the top one is empty, right? Well, it still exists, it's just empty. So what we have here is an anti-bonding empty orbital that the oxygen, in this case, with its lone pairs, that's where it's going to donate its electrons, right? It's going to donate its electrons into that anti-bonding orbital. And then this bond is the one that's going to be breaking. So we call this a backside attack. And what it's doing is giving the electrons we're giving the electrons in the anti-bonding orbital. That means that whenever we look at an SN2 process, we're always adding the nucleophile in an opposite position to the leaving group. Okay? The electrons from the hydroxide are coming in from one side, the leaving group has to leave from the other side. That sets up a few specific things for SN2 reactions. One of those is that if I have, let's say, a nucleophile like this, reacting with a stereospecific substrate, what's going to happen is my product I'm going to get inversion. So the nucleophile has to come in from the backside. In this case, the bromide it's a stereospecific center. It's going forward, so that means when the carbonyl comes in, it's got to come in from the backside. Which causes this stereo center to invert. Now, it inverts. In most cases, it'll change its name, but don't get R and S confused with the inversion of the stereo center. Why? In most cases, the group leaving and the group entering will have the same priority, right? Usually it's going to be a heteroatom with a atomic orbital higher than carbon, right? So therefore, when I substitute, in most cases, it's going to be a direct substitution, and I'll go from R to S and S to R. But I could substitute a high priority with a lower priority and result in no name change, but the stereocenter still inverts. So I potentially could go from an R to an R because I've changed my priority, but the stereocenter still inverts. So don't get the naming convention and the stereocenter inversion separate. They're separate. They should be separate. Okay. Okay, so that's one impact of the fact that we're adding this to the anti-bonding orbital, is that we're going to get inversion, right? So our stereochemistry, oops, is inversion. The other impact of this backside attack is if I have something, this my nucleophile, if all of a sudden I go and do if I change my substrate, and what we're looking at here is, you know, this one is a methyl, this one is primary. So we're looking at the carbonyl, the carbon of the substrate. Right? So we go from fastest, and the reason that the methyl is faster is, we think about it, the backside is where we want to have our reaction, and so there's less substrate. And I'll show a better example, a better picture of that in a second. So there's nothing there blocking out that backside attack. When we go to primary, I have two hydrogens, right, and the methyl now. And here I've got a little bit, right? There's going to be a little bit of interference because the methyl group's going to take up more space than the hydrogen. When I go to secondary, I'll still get a reaction in an SN2 type process. Now here, notice how I'm showing the inversion, right? Here the bromine was on my right side. Here I haven't shown a change in my methyl, but what I've done is I put the leaving group, the new nucleophile, on the left side, right? So I'm showing inversion here without changing the carbon from being backwards to forward. Okay, so it's still inversion. This is going to be much slower. Then when I go to tertiary, we don't see this reaction occurring by SN2. And that's because now we've blocked out that backside, right? So it's sterically hindered. The rate of the substrate for substitution in an SN2 is going to be based on the spatial on the ability of that nucleophile getting into the backside of the reaction. So in the methyl case, right, we had we don't have much impacting. Let me redraw this. That orbital, right? So therefore, we get backside attack pretty easily. But by the time we get to our CH3, our tertiary position, we have no access to that anti-bonding orbital. So what happens is we go from very fast to incredibly slow, right? And the reason we say this is not by SN2 is because do we have a different way this could occur? Yes, and that's the other substitution type, right? In an SN1, it has to attack the backside. Does it have to attack the backside in an the two-step process? No, and that's what we'll show in a second. So the rate of reaction of an SN2 is based on how easy is it for the nucleophile to attack that backside. Right, so we've looked at the substrate, we've looked at the stereochemistry. Right, now let's look at nucleophiles, and the book separates this out, and we'll talk about nucleophiles in a large degree. If we look at a nucleophile, what we want is we want a good small nucleophile. So, you know, things like halides make good small nucleophiles, right? Because they're just themselves. But there's a but. But what do we also know about halides? They're also good leaving groups. Things like hydroxide, right? Things like methoxide, again, I can make it pretty bulky, right? But smaller ones of these are good nucleophiles, but there's a but. What's the but? What do you think of when you think of hydroxide? That's our classic base, right? So they can also be bases. There's also these kind of small. That makes a good nucleophile. This makes a good nucleophile. The one I showed you is still a pretty good nucleophile, the acetate. So for an SN2 to occur, remember that we only have one curve. So really the ability of it to be a good solid nucleophile is important. And what would slow it down? It would slow it down if it's not a good nucleophile. Example would be water, right, versus hydroxide. This is a nucleophile, but it's a poor nucleophile as compared to hydroxide, which is a good nucleophile. So if I wanted an SN2 to occur, I would choose sodium hydroxide over water. The other species that make good nucleophiles are the thiols. So we can make sulfur-containing compounds. Those are strong. Those are good nucleophiles. When we're looking at our leaving group, really we want something that's a good leaving group. We want the products to be more stable than the reactants, right? And so, again, chloride, bromide, iodide, but there's a subtle difference. It turns out the bromide's a little bit better than the chloride, the iodide's a little bit better than the bromide. This has to do with polarizability. We also have things like, you know, this was a good nucleophile, but it also is a good leaving group, right? Because I have resonance. Other things that make good leaving groups are things that are positive. So that's a good leaving group, right? Because when it leaves, what I get is a neutral species. And biologically, you see a proton transfer to make something a better leaving group. You see that alkylation to make something a better leaving group. So we want a good leaving group, right? And then for our substrate, that's what we're reacting on. We want so methyl is going to react faster than a primary, which is going to react faster than a secondary. That'll react much faster, much faster. In fact, tertiaries we usually consider they're not reactive. So one of the things you want to think about when you're looking at these is thinking about putting all this together and comparing. So when we look at an SN2 reaction, the nucleophile is going to react with the electrophile and the leaving group. the rate is going to be equal to the constant times the concentration of my nucleophile and the concentration of my substrate. Stereochemistry is going to be inverted. The substrate preference is going to be methyl over primary, secondary. Nucleophile will want a good nucleophile. Leaving group. Right, we want a good leaving group. So when you're going through these, it's good to learn these all together, right? It's also good to be thinking about why. You know, just don't learn them, but think about why is it that the substrate sterics raise such a big role in this. It's because that backside attack is attacking that anti-bonding orbital, right? And there is no access whenever you block out that backside. So the whole rate of an SN2 is going to be the ability of that nucleophile to attack that anti-bonding orbital. So when we look, yes, ma'am. Not through an SN2. Well, could it happen? Possible, right? Now, will it happen? That's another question. So plausibility versus possibility versus plausibility. Possibility, yes. Plausibility, no. And that's because we have another reaction, right? And the other reaction is the two steps, right? So if we look at a two-step process, now we've got another substitution process that we can look at. You're ahead of me about 20 minutes, but that's good. Okay. So in the two-step process, right, what is happening in the two-step process is that our electrophile and our leaving group have a separation first to end up with the electrophilic being fully positive plus our leaving group. And then in the second step, right, the nucleophile then attacks the electrophile. So in a one-step process, we had nucleophile attacks electrophile, leaving group leaves. In the two-step process, leaving group leaves. And I'm going to put an and, right? Nucleophile attacks electrophile. So we've inverted the two steps, right? First step is leaving group leaves. Second step, nucleophile attacks electrophile. So when we look at our energy diagram here, we go through a high energy transition state, a low transition interstate and transition state, and then we get to our products. The first step is the slow step. Second step is the fast step. So in the first step, that bromide is leaving. What we're going to have in most cases, especially with these substrates, we're going to end up with a carbocation. The height of this transition state here is going to depend on the stability of this carbocation. So in SN2, what was the driving force, right, was the strength of the nucleophile and the sterics, the substrate spatial arrangement, right? How fast that reaction occurs has to do with the ability of the nucleophile to give its electrons to that electrophile and the sterics around the electrophilic carbon allowing the nucleophile to get in to react at the antibonding orbital. In this process, right, in a two-step process, it's going to be driven by the stability of that carbocation, right? If that carbocation cannot be formed, then we're not going to see this reaction going forward in a timely fashion, right? And so what we've done between the one step and the two step is we've changed the driving force, the fundamental driving force between these two, right? One has to do with the nucleophilicity of the nucleophile, and its rate has to also do with the substrate sterics, the spatial arrangement of that. In the two-step process, it has to do with the stability of that first transition state, that carbocation. So stability of carbocation versus space. Okay. Then what happens here is this reacts, and oh, that's weird. And I end up with right the addition of the nucleophile in the second step. So my rate here, if this is the rate determining step, my rate is going to be K times the concentration of my substrate. In this specific example, my rate is going to be equal to K times the concentration of this CH3 bromide. Okay. The nucleophile is in the second step, right? That's not the slow step, that's the fast step. So therefore, the concentration of my nucleophile is going to have no impact on this reaction. If I can double my concentration nucleophile, it's not in the rate law, it's not going to matter, right? If I increase the concentration of substrate, I can increase the reaction. Yes? It's planar here, right? I've still shown it because I'm kind of showing it, the plane's going this way. I'm still showing it here, right? Which I was going to get to, but it actually means that we then have two possible, in this case, they're both the same because there is not a chiral center, But if there was a chiral center, we could get an attack from both sides. So when we're looking at the rate, right, it's only a first order reaction. And that's where this one gets its name, which is substitution nucleophilic first order. Okay, so SN2 has one step and is second order. SN1 has two steps and is first order. And again, you'll get that confused. So please don't. Okay. So we've got a change in several things. Let's talk about the stereo center, right? So when we look at the reactivity here, the first step is going to create, and let's go ahead and, well, we'll use this one and then we'll show you an example. So whenever this group leaves, we do go to the planar carbocation with a p orbital. Right, this is an sp2, so it has a p orbital, and it's going to be that p orbital where we get reactions. So in the second step, when that nucleophile comes in and attacks, that nucleophile could come in from the opposite side, if we look at our starting material. Or it could have come in from the same side. So I could get backside attack to end up giving me, again, there's no stereo centers here. To give me this species, right? Or I potentially could react on the same. So I could do back or same side. Oops. So in an SN1 process, since I'm going through this planar carbocation, I could end up with inversion and retention. Yes, ma'am. Well, if we think about it, this is planar, right? So if it's planar, is there any difference between either side of that molecule? No. Okay, so in these kind of free form molecules, not three-dimensional complex super molecules, right? Just the ones you're going to be seeing most of the time here until you get to medical school, right? Both sides of that are the same. It's like a white piece of paper. You know, no watermark, no nothing. Doesn't matter which side you write on. No. So if you threw a bunch of paper up in the air and you let it fall down and you started writing on the paper, what would be your percentage of writing on the front versus the back side? 50-50, right? And that's what we see here, is we see inversion and retention, okay, tend to be about the same. Now this has to depend on how fast the reaction is, but if we go to a full carbocation, we get inversion and retention equivalent. Right? When we have a mixture, what do we call if we have a mixture of R and S that are equal to each other? A 50-50 mixture. Okay. Well, that's called racemic. So therefore, an SN1 creates racemic mixtures. So if we took this reaction, we got a tertiary substrate, what we're going to end up with is a 50-50 mixture of both retention. Oops, that's not going to make ozonium ion, right? Plus so if we start for an SN1, if we start with a chiral solution,